And I am live now. So welcome everyone to the fourth episode of live coding retracing in a weekend in OCaml. Last time we what? This shouldn't be right. Oh, that's a wrong folder. Yeah, last time we implemented part of the dielectric material, but the problem is it is totally black, so something is horribly wrong, and that's the priority today to fix that. And after that I will finish the rest of this book, which contains that much really. After the electric material, it is positional camera, and after that we have motion blur. Then we render a final scene with some randomly positioned sphere. That's the entire book. So let's start. The last time after I find out the the sphere is totally black, I ended that screen because I don't want to debug on like live and waste your time. And what I find was the error is that this is not actually at the electron materials implementation, but at sphere intersection. So the problem is, oh sorry, I reinstalled the system and my drawing is gone. But the problem, I guess it's hard to kind of demonstrate without any kind of drawing. The problem is currently our normal the normal vector we returned is wrong. So if we intersect at here, the normal returned is right. But when we have the second intersection, when we intersect inside the sphere, we want the normal to return in this way, but actually the normal we currently get is this. I know how to. So the red is the current behavior, but what we want is green. That's the thing we need to fix. The reason is in here we just say normal is basically the normal vector is the position minus center, and then divided by radius is just normalize that value. It's basically always point outward. But what we want is if we intersect the sphere inside from arrays and shoot it inside the sphere, then we want the normal vector to point inward. So that's a problem. And let's fix that. Book have an implementation of this, so I will just copy that. basically, depending on if it's front face or back face, we do different thing. If it is front face, then we know we intersect outside, and our normal is just the outward normal. But if it is back face, then we need to negate this normal. Basically it. Yeah, that should be able to fix this problem actually. And so now this kind of flipped thing looks right. The other thing we need to do is to update our test because our test behavior is wrong. So we are actually testing the wrong thing. In this intersect inside, normal should be flipped. That's good. So we fix the bug. And the next step is to continue implementing the dielectric material. I know how to spell that right. We implemented this part. We implemented total internal reflection. And now let's talk about Schlick approximation. So what Schlick approximation is about? So that's a simple observation of if you have a ray like this and a ray like this. This ray is likely to refract, and this ray is more likely to reflect. This is called Fresnel phenomenon. Fresnel effect. We show some demonstration on that. I think this is a good image of Fresnel, where like when your incident angle becomes smaller and smaller, the reflection becomes stronger. And yeah, this picture is a very good demonstration. Like, look here, the reflection here is very strong because your incident angle is larger, and reflection here is much weaker. So we need to implement that. Fresnel phenomenon itself is really complicated, but there is a very simple approximation that is good enough for most real-time or not real-time, just rendering applications. and it's also pretty fast. So let's do that. So the Schlick approximation is a function where we give it a cosine if the incident and cosine of the incident angle and the refraction index, and then we calculate the result of reflection. We can see here it is not linear, but some kind of interpolation between R0 and 1. If you realize that, because if cosine is 0, then this whole thing is 0, and we just get R0. If cosine is if cosine is 0, then this is 1. So 1 to power 5 is 1. So we get 1 minus R0 plus R0 is 1. But if cosine is 1, then this part is 0, so we get R0. Hope that's clear. I don't want to go too math heavy in this stream. That's why I kind of hand wavy a bunch of stuff, and I just copy the book for the maths because I don't want it to kind of scare off people without math background. I remember the float module have an int power or something. Did you power? No. It is int power. Oh, that's why my auto completion is not working, because we haven't import base yet. So the previous float is from the standard library. I think we also need to open float here. Yeah, settles it. To execute fine. What am I doing? Yeah, the image looks fine. Now we need to do some additional check. First, still we need to check if the like we have total internal reflection. Then we need to check if we we have certain probability of reflection and other probability of refraction. Then we just need to check if get some random uniform floating point distribution, and then check if it's less than that probability. Then we reflect. Sorry. Oh, put stuff in the wrong place. We should, yeah, we already. Else can reflect. Sorry. Else if random number is less than we need to get reflection probability first. And we also reflect. It's not so obvious we done the right thing, because in this thing it's just not obvious. In later, I guess we will postpone to verify this thing work later. So another thing about this kind of like global mutable random numbers is it's impossible to test this. It's just global side effect, how mutating some global states and give you some random number, how to test that. So we will not even test that in this episode, and just assume it will have some really redundant code here. Do this. So my Emacs have this package called prettify symbol or something. That's why my or become this logical symbol. So just be aware of that. It looks right. Yes. This image is too small for me to see what's going on. So let's make it a little bit bigger. I hope it's still fast enough, because our OCaml implementation is definitely pretty slow currently. Looks good. follow us, not in the program, that interested in this. I will just skip this. So we finished our first objective here in 20 minutes. Pretty good. So we implemented dielectric material. Time to it. Got it right. Yeah. Good. Next step, we need to deal with positionable camera. Currently, our camera is like 4 hard-coded value, and our gateway just using those 4 hard-coded value. The first thing we need to do is to have a positionable camera. We actually need a camera type. So what am I doing? Looks pretty decent. And here, when we try to get ray, we pass 1 additional camera here. Accidentally recursive types. That's like programming newbies always will do this kind of stuff, like accidentally discover recursion. And I was course assistant for a while for intro courses, so people will these kind of questions. They just use recursion when they don't even know what they are doing. I was doing exactly that. We also need to create a camera. Currently, we will just keep it all hard-coded. Before, but at least we have a camera type, so we have multiple cameras, not only one. And we use create function to create this camera. Let's run this. Yeah, then notice I put this camera argument at the end parameter, I should say, at the end of the parameter list of getRay. That's because I want to use type operator like this. So for language with autocurring, I personally think data structures should be put at the end of the function signature. But for OCaml, it's not consistently done. Different libraries have different conventions. Especially for standard library, they use like this kind of convention, so it's a bit confusing. But that's my way of doing stuff. And if you are familiar with some other languages, like for example Elm, Pascal, then you can see like people write this kind of thing. It looks fine. So actually we need to actually implement this positionable camera. The first thing they want to implement is the field of view. And with the field of view as an end goal, we can calculate this height by using tangent. And so they have a vertical field of view and aspect ratio, because if we have a screen, then like this, if this field of view vertically maybe like let's say 90 degree, but this horizontal field of view may be a bit larger, 120 degrees. So we need aspect ratio, and we just specify one field of view and one aspect ratio to distinguish us from different vertical and horizontal field of views. So we call it VFOV. I know several libraries such as GLM call this thing FOVY, so I will call it FOVY. And aspect ratio. Notice that this book actually don't have FN types, like proper FN types for points and vectors. Instead, this is just an alias of vec3. So personally think this kind of alias is pointless. You may disagree, so that's why I'm still using vec3 for everything. Later, we may factor these to FN types, but that's probably another episode after we implement all three books, all the features we want. Not all the features we want, but at least all the features in those three books, then we can start to consider those stuff. Also in the book, they pass in the here. They pass in the field of view as degree, which I strongly disagree, because it's just too easy to have a mistake of mixing degree and radius, like different functions. Some function expect degree, some function expect radian, and you don't know what's going on. Everything is a mess, and I myself get bad by a few times. So if you go to like the more strongly typed routes, then the first thing you want to do probably is to put two modules, one called degree and one called radius, and then like just degree type and radian type can kind of converting from each other, and then we just use radian for everything. For here, I don't want to get that yet, but still we'll just use radian for everything, even though it's just a float. Because mixing degree, then the API get confusing, and I ever have no idea if I'm using degree or radian. And the thing I know is standard library vendors for all the languages almost always use radian. So just ignore degree, basically. Don't use degree, you'll be fine. That's why we don't function here, because we always use radian. That is what I was talking about the aspect ratio, is the aspect ratio times height is the weight. All those information have origin. All those information we know enough to those three left corner. Okay. So now our camera expects those two. Yeah, our camera expects those two things here. So personally, I think those arguments get a little bit confusing. So I will use named argument, because our parameter list will soon get longer. (90° is pi over 2). As we said, we will never use any of the degree stuff. We will just always use radian. Aspect ratio be like divide by of int height. But yeah. Oh, that's interesting. Did I not build that once before so that there's a syntax error to just get there, stuck there. That looks right. Oh, or our thing just looks downward for some reason. For 90-degree. See if I did something wrong. This function. But yeah, camera is also another pain point to debug. Also, all those kind of things are really hard to test. And you can try to come up with some test case, but like it's time consuming, so I will at least not do it now. So this kind of thing is an example of not fit for test-driven development, even though I really like that technique because it's just so hard to come up with test cases for numerical stuff and to verify that test case work in the first place. Unlike like previously we were testing the wrong thing, right? So you can see this kind of thing is tricky. Virgin. Do have negative? Uh-oh. I should fix it. Yeah, so our image does not change at all, but if we change our field of view to something stranger, then we will have a really narrowed field of view here. Yeah, we basically just look at this green ball because our field of view is so narrow, it's only 20 degrees. Now we want to actually put position and orientation of the camera. The book adds 3 parameters to a parameter list called look from. So the point camera looking from is also the origin of the camera. Look at and up direction. So if you like did some kind of matrices, just graphics programming in general with homogeneous coordinate before, you may find those kind of things really familiar because there is a function in libraries like GLM, for example, called lookAt, and take exactly those 3 parameters and return you back homogeneous matrix, and then you can use this matrix to handle the transformation of all those stuff. That's certainly more convenient than our current implementation, but we don't have matrices. Also with the OCaml, I certainly think if we just implement matrix naively, it will be slow. So we also just use what this book do is manually put these 3 in. So the problem, of course, is our parameter list gets a bit ridiculous. So VUp, this VUp parameter is like view up direction, but what we're trying to get is also normal coordinate for the camera. So like three kind of uh, also normal vectors, all like in the right direction to all are like 90 degrees to each other, but we don't know how to provide an up vector yet. So this VUp is not the final up vector. We will calculate final up vector with a series of cross product because this is 3D, so it's higher dimensions. We need to use something called Gram-Schmidt to get also normal basis. And unfortunately, for a long time, I just gave all those knowledge back to my linear algebra professor, so I don't even remember how to do this. But for 3D dimensional space, using cross product is enough to get us orthonormal basis. And so if you heard people saying computer graphics is really math heavy, sure, but a lot of things have shorthand. Like you don't need to really know in depth in linear algebra to start doing stuff. You really just fiddle in with 3D, 4D, 2D stuff. 4D is for the homogeneous coordinate stuff. It's really 3D with the additional homogeneous dimension. Like, not really a dimension. Those three, we need to change. Origin is now round vector, a point. It is a point. And this should minus origin. Book didn't highlight that. This line gets a bit long. First, this like WUV is our final orthonormal coordinate system. W itself is just like this stuff. I don't know how to clear this stuff. If we have a camera, W is this direction that like direct to where we want to look at. So that's why this is a lookat point minus look from point, and because it's a direction, we want to normalize that. And we use two cross product to get also normal coordinate system using our VF vector and the previous W. No. Lower left corner false, because we need to consider a bunch of more informations for the each of those here. Never used it. Ah. Yeah, we need to provide all of those. Look at up. Yeah, maybe the specific street 010 because in our world use y up. It's totally reasonable to use the app. That's a convention used in the book. Following that. Do it right. Wow, that's slow. Really? Oh yeah, that's slow. something horribly wrong? This shouldn't happen. Let's try again. And then by using probably we are looking directly at the glass ball or something. Yeah. Sometime. Yeah. What? Sorry. Nothing. It's camera, folks. So camera for you. You need to debug this crap. Not always easy. See what's wrong. Make sure here is right. $90. Right. So look from minus look at. So use opposite vector for the W. And our whole also normal base should be just flipped, and we are looking at the exactly opposite direction. See, no, yeah, that looks right. I think the next step is, yeah, they kind of zoomed in, see what's going on. So we also do that. I don't know, sometimes Emacs has a bit of lag for image viewing, so yeah, it's something like fine. Now let's implement our final feature, the focus blur. If we can finish this thing before 2 hours, then I will try to do some factoring. But if it is not possible, if I just implement this thing for an hour, stop there. And next time will be purely refactoring. Before we start next book, I want to put this a bunch of cleanup. Position. I don't. Okay, positionable. Is this even a word for this? Okay, it is. So after this, we still have like final scene to render. So I think we don't have time for refactoring today. I will do it next time. So the reason for this kind of defocus blur is basically because our camera is not a pinhole camera, but something like lens. It's actually way more complicated than that. A better approximation is something like that. It's still approximation, but way better. But we will treat it just like one lens, because that's easier. Because it's cheaper. So first first so first when we generate sample rays, we will have this kind of little bit of jittering to mimic the behavior of defocus blur to be in camera. No comment. Okay, good. Oh, I hear something. So this piece of code is interesting. While loop, okay, OCaml have while loop, but OCaml don't have continue. So what can we do with this piece of code? This piece of code is we get some random vector, and if it satisfies some condition, then we just return that. Otherwise, we continue to calculate, get random vectors until we get a satisfied one. And I think the easiest way, this one is just hand roll a tilde function. It's pretty trivial. We can also go with fold, and then we need some kind of generator. Not do that. Not even fold. I don't even know. I need to look at the standard libraries to decide what to use. And if I just write the tilde recursive function, then it's trivial. It's real one and 0. Don't even know why they use X3. All I need is those 2 points. Because I'm following that book now, and there can be an opportunity to factor. Greater than 1, continue means we need to do this again. Else we just split in this point. Morphic comparison is bad. OCaml don't have any kind of comport and ad hoc polymorphism, so basically, if you use OCaml, you think about you need to polymorphic comparison, polymorphic operation. Also, the cost. So this kind of. We have this field call here. We need 2 more of aperture and focus distance. aperture is just like how big the lens is. So like, let's say if this aperture of this is 1, then like this is probably 2. Just simple concept. And focus distance is for our lens. This distance, what's the focus point from the center of the lens to this, to this focus point? What's the distance? Parameter, yeah. Need to go away. This line also gets ridiculously long. Let's need focus distance for basically. And then we need to record this information now. Also normal coordinate, because we need to use it in this getRay function, and also the lens radius. Yeah. Add those. Here are vectors. We're doing lens radius is a floating point number. Where the W, U, and V. I'm probably using Emacs in some really inefficient way. I am currently reading a book on mastering Emacs. I just read like few pages. It already tells me tons of stuff. Just like, use this editor for almost 5 years, and how inefficient I am using it. I definitely need to do some work on it, like using less mouse, actually navigating better. And in here, If we add offset to origin, so this the camera can use UV. It's a bit confusing because we use UV for two different stuff. The book actually at here named the parameter to SLT, which make a lot of sense. I will keep it UV because OCaml we don't have this kind of name collation problem. Origin minus offset. Good. Please read. Temperature is 2. That's a large temperature consider how close we are. Focus distance is calculated from log find log at. Yeah. Everything. Okay, so we have our hi Max. We have a blurred image implemented. That's quick. Be quicker than I imagined. Yeah, let's meet. This final thing is just adding a lot of stuff basically. Instead being fixed, here we still have a bunch of fixed. The first is just one. Probably just two. No, 1, 0. Index. It's actually just below. I don't. Index is 1.5. There's 3. 4, 1, 0. So we have all our fixed. Here set up the changing camera. I just want to do quick test. Those 4 spheres kind of displayed, and then we can add those renders. 13 to 3. There's a way smaller aperture in this one. Not be that blur. that feel wrong? Yeah, it is. So we have our 4 spheres set up for fixed sphere, then we need to add all those random things on top of it. -11 to n again with I. We use this number I in many places in this code. No, you're stupid. I guess that will be an issue later. Just one line of fix and kind of nested loop generator style. We just use this kind of thing again. Also notice in OCaml you can just name shadowing like crazy. Also it's same in some other languages. For all the ML languages, because let binding, the property of let binding is can shadow the previous binding. Good thing or bad thing, I think it's a bad thing, to be honest. Yeah, that's just how it works. It's inclusive by expect something here. I just want to see what those thing is. Nine. It's not intrusive. that's better. So we implemented this auto loop part. We need a float here, not have taking the camera. I think no, it's just on roast or warnings. Is integer, right? G and I, so let me use the same naming convention. Oh, this part is probably really boring. Just pretty the same. So after this, I will try to find the point I get the final image, and then in the description of the video, I will. But here you can find the final image. We cannot use float because naming conflict, and open float before thing, but let's just not do that. And don't have. Let's do that. And something. And we pick material. This kind of comment is quite redundant. Like add material just after. So we need a vec3 random vector. No. Let's put it here first. And the vector. It's just 0 to 1. Yeah. almost all the sphere will be Lambertian, and the rest, almost all of them, will be metal. Keep typing in when I want to type again. So they have let's do some now. Definitely refactoring candidate. All the whole thing is refactoring candidates. Like this function, a really bad name. Better call it like, I don't know, uniform max-free distribution or something. Have more consideration into that stuff. It's a new uniform distribution in a cube. This function basically. At least if we implement it more general, because currently we just fix 3D cube from 0 to 1, but we can think about it can be more general. It can be a cube from 0 to some arbitrary value. Meaning will be class. Don't use B at all. This is here. Makes more sense. It's kind of like a bunch of spheres is distributed on the grid with some kind of jittering. The reflection index of the electric material, which is hard coded into 1.5. Good enough. I think that's it. That's our scene creation. So let's run this. we do something wrong in this line because teams just don't add anything to it, basically. And going on with no, because yeah. Looks right. Then we are adding those spheres out there. All gone. This definitely don't look right. And I add 100 sphere that executing that fast, it seems. Oh, returning the same with function just not get at all. That's why I said name shadowing is bad because it just made everything kind of confusing basically. They're a lot slower, and that's probably a good sign. Let's wait for the final image. I will not render high resolution one in the screen, but afterward I will render one and put it in the repo. Okay. Let me see if I have any chat. Not really. Okay. Good. This look exactly like on the book. So that's it, guys. We implemented retracing in Weekend book in four live streams. Next time we will be a refactoring episode, just trying to kind of clean up a bunch of stuff and tidy up those ugliness. And the time after that, we will start working on the second book of retracing next week. So the second book, motion blur on the value hierarchy, which is accelerating data structure, that can be important to for performance. Otherwise, everything just too slow. And texture, noise, yeah, I don't even know if I want to do this or not. Maybe yes, because the point of this stream is to implement this book. This stuff is kind of boring, noise detector and image detector. Rectangle and light, with that we can do the classic mailbox. Okay, that's it. Thank you for watching this episode.